I like to start this section with something of a puzzle. If you wanted to add together all the numbers between 1 and 20, you could do it this way. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, and so on. And that would take a while, but you could certainly do it. But here's another way to think about this problem. Let's take the 1 and the 20 and add them together. And then the 2 and the 19, and the 3 and the 18, and these all sum to the same thing, 21. At that point, we can say, well, how many of these sums do we have? There are the first three. 4 and 17 would be another one. 5 and 16. 6 and 15. 7 and 14. I'm going to go up to the top. 8 and 13. 9 and 12. And 10 and 11. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 21s. So the sum of 1 through 20 is 210. Not only that, but notice that the number of terms we had that added up to 21 was half the number as the number of items in the list, assuming that that last number is an even number. The first person ever credited with using a strategy like this was Carl Friedrich Gauss, way back in the late 1700s. Apparently he was an elementary school student, and his teacher, finding him particularly annoying, gave him a sum to do to keep him busy. He was asked to sum the numbers 1 through 100. So imagine my list here, but with 1 plus 2 plus 3 and so on, all the way up to 100. And the teacher thought, well, that'll keep him busy for a while and keep him out of my hair. But about a minute later, little Carl turned around and said, "Excuse me, sir, the sum is 5,050. Oh, by now you've probably figured out how he did it. He added 1 and 100 to get 101, and then 2 and 99, and 3 and 98, and so on. And he realized that he had 50 copies of 101. And that's just 5 times 101 times 10. At any rate, while this annoyed the teacher even more, Carl Friedrich Gauss went on to be one of the best-known names in mathematics. The point of the story and the point of the puzzle is really just to kind of show a strategy here. It motivates what we're going to talk about in this section, but we don't really need it in order to do that. What I will do is use the sum of 1 through 20 that I originally had written on the screen to show you another way to write a really long sum like that. What I want to do, and what I want to somehow capture, is the idea that I want to add up all the numbers starting with 1 and ending with 20. And of course I should specify that the numbers that I want to add up here are integers. Well, my starting number is 1 and my ending number is 20, but I want to find a really shorthand way of conveying that I want to add these numbers, not multiply them or apply some combination of operations. Historically, the symbol that we use to do this is the capital Greek letter sigma. Now, just as it stands, this kind of appears to say, well, if sigma means add and you start at 1 and end at 20, that should be enough. And for a simple sum like this, it probably would be. But over the centuries, we've evolved this notation to be able to do some much more difficult summing problems. So we've added a few things to clarify. For one thing, I'm going to say that I want to add up the number I as I goes from 1 to 20. That I is called an index. It just says sum up this thing right here, I, starting at 1 and ending at 20. The other thing that's got added is we put down at the bottom, instead of just assuming that you know to start at I equals 1, we explicitly state I equals, so now what this says is take I, right here, and add 1 plus, that's the sigma, the next number, which is 2, the next integer, plus the next integer, until you get to 20. So this sigma notation, sigma I equals 1 to 20 of I, means the same thing as 1 plus 2 plus 3 all the way up to 20. These two things mean the same thing, but the summation notation, the sigma notation, is much more compact and takes a lot less time and effort to write than the entire sum. Now imagine that you had to write out the sum of all the integers between 1 and 100. And I don't mean 1 plus 2 plus ... plus 100. I mean you have to write them all out in the same ways that I have 1 through 20 written out up here. That would be tedious in the extreme. But now we have another way to do this, or at least another way to represent it. The Greek letter sigma, underneath we'll write I equals 1. At the top we'll write 100. And off to the side we write the I. And this just says add up all the integers starting at 1 and ending at 100. Now, this doesn't help us calculate that sum, but it is a much more concise way to write it. What if you were asked to do something like this? Add 3 cubed plus 4 cubed all the way up to 9 cubed. We can use sigma notation to do this as well. What I'm going to do is notice the thing that's changing. 3, 4, 5, 6, 7, 8, 9. And the thing that's staying the same in each term, which is that the term is being cubed, or that the number in the term is being cubed. With those two pieces of information, I can write my sigma, and then I at the bottom equals 1, but not 1, because I'm not starting at 1 this time. I equals 3, and I'm stopping at 9, so I'll put a 9 at the top. And then I'm going to take the thing that's changing here. This is 3, 4, 5. I'm going to use the I to represent that. And the thing that's staying the same, the cubed, goes there. So what this notation now says is, starting with the number 3, cube the number, and then add cubing the next number, and cubing the next number, and cubing the next number, and so on, until you get to cubing 9. Again, it's worth pointing out that this doesn't help us compute the value of this sum. It just helps us write out the instructions in a more concise way. If the sum is small enough, you can still just use arithmetic or your calculator to figure out what the result would be. All right, let's see if you can do one. Compute the sum represented by the sigma notation. I goes from 2 to 6 of I over 2. So you're going to take I equals 2 and plug it into I over 2. And then you're going to take I equals 3 and plug it into I over 2, and so on, and add together the results. How did you do? You should have I over 2 for each of the following integers. 2 over 2, 3 over 2, 4 over 2, 5 over 2, and 6 over 2. We're going to add these together. We're starting with 2 over 2 because the problem tells us to start with I equals 2. We're stopping at 6 because the problem tells us that that's our last number. All right, working out what this is, I can simplify 2 over 2 is 1, 4 over 2 is 2, 6 over 2 is 3. I'll fill the other terms in here. 1 plus 2 is 2, 2 plus 3 is 6, so if I add the whole numbers together, I get 6. And adding together the 3 halves and the 5 halves, I get 8 halves, which is 4. So my answer is 10. Is that what you got? You might be wondering why we're doing this particular topic in a course on calculus. Well, it turns out that in order to represent some of the area problems that we're going to be working on next, we need to know how to write out the sums in a concise way. Some of the sums in the next topic would be very long indeed if we didn't have a shorthand way of writing them out. As you've just seen, it's not always just I that gets added up. The I over 2 in the previous example is like a representative term. The generic notation that we use for such a term is a sub I. If my problem looked like this, I goes from 1 to 5, and we sum the terms a sub I, then my sum would look like this: a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. And we don't know what a is in this particular case. This is just a generic sum. We can use this notation to make some other observations. To start with, I'm going to generalize this even more. Let's say we want to sum a sub I as I goes from 1 to some generic number n. That makes our sum look like this: a sub 1 plus a sub 2 plus a sub 3. And I don't know what n is, but I can always do this: plus up to a sub n. Sometimes, to indicate that we know there are multiple terms in the list, you'll see a sub n minus 1 and then plus a sub n. Sometimes summations are written like that, and sometimes they're written just with plus a sub n as their last term. But it's good to have seen both representations. Now, let's take a look at some examples of things that you can do with summation notation, some properties. If instead of just adding up a sub I, you're adding up like 3a sub I, then your sum would look like this: 3 times a sub 1 plus 3 times a sub 2, the second term, plus 3 times a sub 3, and so on, all the way up to 3 times a sub n. Well, if that's true, then you can factor the 3 out of the sum that you've just written, and you would have 3 times all of the sum a plus 1 times a plus 2 times a plus 3 up to a sub n. But a sub 1 plus a sub 2 plus a sub 3 and so on is just the sum as I goes from 1 to n of a sub I. What this tells us is that if you have a constant factor in the thing that you're adding up, you can bring that out in front and just do the summation of the terms inside and multiply the result by that constant. I'm going to write this in the top right hand corner of the screen, and we've got a few more properties to look at too, so by the time we're done with this, we should have a list of properties we can use going forward. Remember that a sub I is a generic representation of the term of whatever the sum is. Well, c is just a generic constant. I used 3 in the previous example, but any constant would work. All right, let's take a look at another one. What if all you had was a constant? In other words, what if I summed from 1 to n just 3? Well, that means take 3 and add it to 3 and add it to 3. There's no I in my generic term here, so there's nothing that's changing. Everything in there is staying the same. So there's nothing to change from one I to the next. I'm just going to keep adding 3 to itself over and over again until I've done it for n terms. Well, again, I could factor out the 3, or I could just use my knowledge of multiplication to say that this is n times 3. So another property we have for summation notation is that if I have some constant inside the sum, as I goes from 1 to n, then that's going to be the same as n times whatever that constant is. Again, in the previous example, I used 3 for the constant, but it'll be true for any constant. Here's another property. Let's take the sum as I goes from 1 to n of the sum of two things, a sub I and b sub I. In other words, I'm going to take a sub 1 and b sub 1 and add them together. And then I'm going to add to that a sub 2 and b sub 2. The I is changing from 1 in the first term to 2 in the second term to 3 in the third term, and so on. And I need to do this all the way up to the nth term. Well, I can rewrite this too. I can rewrite it as a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. And to that I can add b sub 1 plus b sub 2 all the way up to b sub n. I can get away with that because addition is commutative. I've just changed the orders that these terms are in. But let's take a look at this sum of a sub 1 plus a sub 2 and so on. That's just the sum as I goes from 1 to n of a sub I. And here, that's just the sum as I goes from 1 to n of b sub I. So here's another property we can add to our list. The sum as I goes from 1 to n of the sum of two generic terms is just equal to the sum of the sum. Now let me clean those up. I equals 1 to n. I equals 1 to n. It's easy enough to show the same thing holds for when there's a difference of two terms, so we can stick a minus in there as well. One more property for now. If you take a sub I and sum those terms from 1 up to, let's say we don't get as far as n, let's say we only get to k. But then you keep going, because this says to sum all the way up to n. The next term after the kth term would be the k plus 1th term. And the next one after that would be k plus 2. So this is 1 more than k. This is 2 more than k. So we've just kept going. We've gone from 3, and in here we have 4, 5, 6, as far as we need to go to get to k, whatever the kth term is. And then we keep going 1 more than that, 2 more than that, and so on. And we'll keep going until we get to a sub n. Now, why would I do that? Well, it may not be clear why any of these properties are important, but in the next topic they are going to be important. So with this last one, what I'm going to do is just show that this summation notation here can be written as the sum as a goes from I to k. That would be sigma of a sub I as I goes from 1 up to k. And then this one here says take a sub I and add it up, add those terms up, starting with k plus 1 and go up to n. And we're going to add those together. So the property here is that the sum as I goes from 1 to n of a sub I can be split up into two sums. We can go from 1 to k, for example, and then starting at k plus 1, one more term than this one here, going up to n, carry on summing. That's all that says. So here's a list of some properties that are going to be very useful. I've added a few more to the list. These are a bit more complex, and they take some effort to prove, but they'll come in handy to just use as sort of identities when the time comes. If you just take I, which is the very first thing we actually started with, and add up all the terms, all the integers, going from 1 to n, even though we don't know what n is, we can write this sum as a finite term, n times n plus 1 all over 2. That's really handy to know. If you square I and add up all the integers squared from 1 to n, you get this expression here, n times n plus 1 times 2n plus 1 all over 6. And the sum from 1 to n of I cubed, well, that turns out to be equal to n squared times n plus 1 squared all over 4, which I remember because it's exactly the sum of all the terms from 1 to n of I, that whole thing squared. Some summation problems are easier to do if you use one of these formulas. For example, if I wanted to find the sum of I cubed minus I squared as I went from 1 to 6, then I would say, first of all, using the property that I can split up my two terms, I would say that this was equal to the sum as I goes from 1 to 6 of I cubed minus the sum as I goes from 1 to 6 of I squared. From our last two properties here, I know that this is equal to n, which in this case is 6, so I'll have 6 times, and that's squared for the cubed property, times the quantity n plus 1 squared. Well, and again, n is 6, so I have 6 plus 1 squared. That's all over 4. And from that, I'm going to subtract the property for I squared, which is n, which is 6, times n plus 1, which is 6 plus 1, times 2n plus 1, which is 2 times 6 plus 1, and that's all over 6. And now I actually have a finite sum that I can work through. I've got 36 here. 7 squared is 49. That's all over 4. And from that, I'm going to subtract 6 times 7 times 13. 2 times 6 is 12 plus 1, and all of that is over 6. If I do some simplification here, I get 6 and 6 cancel, 36 and 4 cancel, leaving me with a 9. 4 goes into 36 9 times. And the rest I'm just going to do in my calculator. So 9 times 49 is 441, and the denominator was gone there. 7 times 13 is 91, and when you subtract those, you get 350. So the result of this summation here is 350. So here's a list of all the summation notation properties we've learned so far. These are worth writing down and keeping handy, maybe on a note card or inside the cover of your textbook. We'll be using many of these properties in the next topic. See you there.